off as we take a deep dive into NASA's Space Shuttle program.
A fascinating choice.
Those shuttles, I mean, they just scream space exploration, don't they?
I don't think there's anything quite like seeing a vehicle return from space and land on a runway ready for another mission. It captures the imagination.
Right. Although I have to admit, most of what I know about them is pretty surface level, launches, landings, those amazing images we all know. Maybe a vague memory about a disaster or two.
Right, great.
But how those missions actually worked, the behind-the-scenes stuff, that's what we're going to uncover today.
Exactly. Today we're going beyond the typical headlines and astronaut bios.
Yeah.
And really trying to understand the intricacies and the challenges that the crew and engineers had to overcome.
And to help us do that, we have excerpts from the Shuttle Crew Operations Manual.
Oh, wow.
And trust me, this is not your average instruction booklet.
I can imagine.
This is the real deal. This is what the astronauts used.
That's incredible. Just to give you an idea of the complexity we're dealing with here. Just for one of the space shuttle's main engines to start, over 1,000 valves needed to work perfectly.
1,000.
One engine, 1,000 valves. That's what we're dealing with here.
Wow. Okay. So the manual starts off by breaking down the orbiter structure. And let me tell you, there are some seriously surprising details in here. Like, those iconic pictures of Earth taken from space?
Of course, yeah.
From the shuttle windows?
Yep.
Well, those windows weren't just for sightseeing. They were actually critical for specific tasks, especially during things like rendezvous and docking.
Oh, absolutely.
Wait, hold on. So the crew actually used the windows to help them dock with other spacecraft. I always assumed they just used computers and instruments.
Well, while those obviously played a vital role, visual cues from those windows, especially with the speeds they were dealing with, were essential. Imagine trying to line up two spacecraft, both traveling at thousands of miles an hour, using only instruments. The windows gave them that extra visual confirmation.
That is wild. It's like those windows were multi-tools for space. And speaking of multi-tools, this one blew my mind. Even the heat shield tiles weren't all the same.
Oh yeah, that's right. The thermal protection system was a marvel of engineering. It wasn't just a matter of slapping on some heat-resistant material. It was about precision and understanding thermodynamics. Different types of tiles, each one made to withstand specific temperatures.
Okay, hold on. Different temperatures. What does that even mean?
So during re-entry, the shuttle experienced the most intense heat at its nose and the leading edges of its wings.
Okay.
Those areas could reach temperatures of up to 2,300 degrees Fahrenheit.
Wow.
To combat that, they used black tiles made from a material called, get this, fibrous refractory composite insulation,
Wow.
FRCI. And these tiles could withstand the most extreme heat the shuttle would encounter.
So they color-coded the most heat-resistant parts of the shuttle?
Exactly. The color coding helped the engineers during assembly and inspection make sure each one was right where it needed to be.
Wow, that's incredible. And here's where it gets really interesting, at least to my inner control freak, the pre-launch sequence.
Okay.
I used to think those Hollywood movie countdowns, they were tense. But reading through this manual, let me tell you, a walk in the park. We're talking hours of meticulous checks, tests, procedures.
It really was an incredibly carefully choreographed dance. Hundreds of systems, all needing to work in perfect harmony.
Right.
And the crew, they weren't just along for the ride. They were active participants in almost every single step.
So you're strapped into this incredibly complex machine. You've been through hours of checks. It's launch day. You'd think the hard part's over, right?
You would think so.
Yeah.
But, reaching orbit, that's just the start of a whole new chapter.
Really?
Yeah, in many ways, that's when the real work begins and the real challenges.
Because even once you're up there, things can still go wrong.
Oh, absolutely.
And the manual does not shy away from that. There's a whole section on emergency procedures, which I have to admit, that's the part that really caught my eye. What happens if something goes wrong when you are thousands of miles above the Earth?
Well, that's where all that astronaut training really came in. They weren't just pilots. They were highly skilled problem solvers, trained to think on their feet and react to unexpected situations.
So it wasn't enough to just know how to fly the thing. They had to understand how it worked.
Inside and out, yeah. The manual actually outlines a huge number of potential failures. And we're talking everything from like minor glitches to major system malfunctions.
Oh, wow.
The astronauts really needed to understand the science and the engineering behind every single system so that they could diagnose problems, implement solutions in real time.
So it's like being, I don't know, like a mechanic, but instead of fixing a car in your garage, you're trying to fix a spaceship in orbit around the Earth.
Exactly.
Were there any, specific examples that really stuck out to you from the manual?
Yeah, there were a couple. So one scenario that I think highlights the need for quick thinking was an APU underspeed. So remember the auxiliary power units, we talked about them a little bit earlier, they provide the hydraulic power for all those critical functions.
Right, like steering, landing gear, that sort of thing.
Exactly.
Mhm.
Especially during crucial moments like landing.
Right, right.
An ATU underspeed basically means one of those units isn't providing enough hydraulic pressure, and if it happens at the wrong time, it could be really, really bad.
Okay, so what happens? What do they do if an APU underperforms?
Well, the manual actually outlines a specific set of procedures for dealing with that exact scenario. So they might try and switch to a backup APU. Or they might even try to manually adjust the fuel flow to try and compensate.
Wow.
It all depends on how severe that underspeed is and the circumstances of the mission.
That's wild to think they had to, like, map that out for every little thing that could go wrong.
Absolutely. And it wasn't just about reacting to failures, it was also about anticipating them. Like, for example, there's this thing called an ET separation inhibit.
ET separation, that's when the shuttle detaches from that giant fuel tank, right?
Exactly. After those solid rocket boosters burn out, the shuttle continues going up, powered by its main engines, which are fueled by that massive external tank, or ET. But at a certain point, the ET is jettisoned. It falls back to Earth.
Right, because you don't want to carry all that extra weight into orbit.
Exactly. But that's where this potential problem comes in. So if there's an ET separation inhibit, the shuttle can't detach from that fuel tank.
So they're stuck to this giant, essentially empty fuel tank hurtling through the atmosphere.
Yeah, it could get a little dicey.
That sounds problematic.
Yeah, an inhibit like that could be caused by a bunch of different things. Faulty sensor, a mechanical failure, even a software glitch. And if they can't separate from the ET, well, the consequences could be catastrophic.
Yeah. What do they even do in that kind of situation?
So the manual, it outlines a whole bunch of troubleshooting steps. The first thing would be to try to identify what the root cause is. So if it's a sensor issue, they might try resetting the system or switching to a backup sensor.
Okay.
If it's mechanical, there might be a manual override they can try to engage.
So it really is like this high-stakes puzzle they have to solve, and with very little room for error.
Absolutely.
What happens if they can't figure out what's causing it?
That's when things get really tricky. They'd have to make a choice. Do we continue with the mission and risk it?
Mm.
Or do we initiate a contingency abort, which would mean a much steeper and much riskier descent back to Earth?
Wow. That's a high-pressure situation. It really puts into perspective the incredible skill, the bravery of those astronauts. You know, reading through this manual, it's clear that it's not just about piloting skills. It's about being a systems expert, a mechanic, a problem solver. It really challenges our image of what an astronaut is, don't you think?
Absolutely. And it also speaks to the immense amount of teamwork that went into each and every mission.
Totally.
This collaboration between astronauts, the engineers, everyone down at mission control.
It really drives home the point that spaceflight isn't just about individual heroism, it's about collective ingenuity, this shared commitment to pushing the boundaries of what we can achieve.
Exactly.
You know, it's funny, we talk about pushing boundaries, but this manual, in a way, it represents a boundary itself.
Oh, interesting.
It's that line between, I don't know, the almost impossible complexity of spaceflight
Right?
and the astronauts who somehow climb into these machines and make it all work.
It's really a bridge, isn't it? It takes all this theory and puts it into practice,
Mm.
all based on meticulous planning, rigorous testing, this respect for, well, the unforgiving nature of space, you know?
Totally. And it's not just spaceflight, is it? This idea of a manual or a set of guidelines, a shared body of knowledge that applies to so many things we do.
Without a doubt. Think about anything that's really complex, like, I don't know, building a skyscraper, or even just like baking the perfect loaf of sourdough bread.
Right.
There's always some kind of set of principles, techniques, best practices that guide the process.
And those guidelines, they're not static either. They're always evolving, being refined, updated as we get better, as we learn from things going wrong.
Exactly. And I think that's part of what makes this deep dive so interesting. This manual, it's not just a historical document. It's like a snapshot of human ingenuity in action.
Yeah.
It shows how we, as humans, how we take these complex challenges and push ourselves to achieve things that seem impossible.
Speaking of pushing boundaries, there's this one detail in the manual that really stuck with me, that part about the transition to atmospheric drag models during landing.
Oh, right. Yeah.
It really piqued my curiosity.
Yeah. That's a fascinating part of the landing sequence. As the shuttle's coming back into Earth's atmosphere, it goes from being, this spacecraft relying on its engines and maneuvering thrusters to basically being a glider.
Wow. So they're not using rocket power anymore. They're using the Earth's atmosphere to slow them down.
Exactly. It's this delicate balance between physics and aerodynamics. As the shuttle descends, it's encountering more and more air resistance or drag.
Okay.
And the guidance system has to account for all of that, the drag, the wind speed, air density, even the runway surface, to make sure it has a smooth, controlled touchdown.
That's incredible. It makes you appreciate the level of precision needed to bring one of those things back to Earth in one piece.
It really speaks to the pilot's skill and the sophistication of the guidance systems, all working together. And it all comes back to this manual, this treasure trove of knowledge that guided every single step.
Absolutely. Well, there you have it, a deep dive into the Shuttle Crew Operations Manual.
A fascinating journey.
We've gone from launch pad to orbit and back again.
We really have.
We've explored these intricate systems, these daring maneuvers, all the meticulous planning that made these missions possible.
It's quite a story.
And if there's one thing I hope you take away from this, it's that sense of wonder.
Oh, absolutely.
That appreciation for what we can accomplish when we really set our minds to it.
I hope this has sparked some curiosity in our listeners. I hope they feel inspired to learn even more, explore some of these amazing stories behind humanity's greatest achievements.
I love that. Well said. Until next time, everyone, keep exploring.